And these instruments range from a CT or MRI that you would see in a hospital. GE or Siemens makes a lot of this equipment, to very, very high-end exotic machinery used in national labs and CERN and places like this. So up there at the top, that's the advanced photon source at Argonne National Laboratory, and this is a synchrotron radiation light source. And this is something that produces, I guess not the highest resolution imagery, but a lot of it, and how to deal with that comprehensively is a very, very interesting topic and subject of a lot of research at Argonne. I guess something a little bit less exotic, but more commonplace in chemistry and physics world is X-ray crystallography. You're basically freezing a protein structure or some other structure, and then you're looking at an X-ray image of its wave function. Then at a slightly higher scale, you have transmission electron microscopy. I mean, you can get some enormous molecular data out of these sources. Then you go up a little bit higher scale, you have confocal microscopy, and we use that for brain imaging and techniques like that. Then we have something fairly close to home. We have camera imagery from digital cameras. That's, I'd say, a very significant source of data, especially nowadays that we have RGBD cameras where they capture depth as well. So these will generate very, very large point cloud data, and we have to have some way of dealing with that. Then you have, at a still larger scale, the sort of ultrasound, CT, MRI, the medical devices that are really imaging a human as he's living and breathing, hopefully. And then if you go up a scale beyond that, you are into telescoping scale. So there you talk to astronomers, and they talk about 100 megabytes per second, per day. 100 gigabytes per day coming out of the Hubble Space Telescope, but I think there's a new one, I believe in Australia, that is putting out something like 2 orders of magnitude greater than that. These are enormous sources of data. Again, mostly RGBD data, so where you have, or sometimes a wavelength of light and then the depth channel. So you ideally like to turn this into some three-dimensional model. So data representation. So I think if there's one concept that sort of ties together all of scientific visualization and probably scientific computing, it's the concept of a field. Mathematically, a field is well defined. It's a set of elements, often a finite set of elements that have addition and multiplication operators, which satisfy the field axioms. And, these are very familiar to anyone who's had math as an undergraduate. Associative, commutative, distributive, has an identity and an inverse. So a field is very, I would say, very well defined, but it's also very, very vague and generic. And intuitively, when we think of fields in physics and also in visualization, we tend to think of a varying quantity that's defined continuously over space. So something where you can pick any point in R3 or R2 or whatever domain you're looking at, and this element will be well defined at that point in space. With a 2D domain, I think this is the easiest way of just showing what it looks like. For a scalar field, well, this is a sort of continuous color map of what the scalar would be, but really the scalar would just be a bunch of single numbers at discrete points in space. I actually have that later on in my slides. The vector field would be a set of vectors with varying magnitude. And you have all sorts of ways of visualizing that, but probably the simplest are just these hedgehog glyphs where you show the vector pointing in a certain direction. Then you have a tensor field, which gets fairly exotic. Here, all of a sudden, you have a matrix at each point, or several vectors defining a matrix, and you want to actually have a way of displaying this. And we'll talk about vector and tensor field visualization in 2 lectures down the road. But so today we'll mostly be talking about scalar field visualization. In addition to scalar, vector, and tensor fields, you also have this concept called multi-fields. And this is actually, multi-fields are really just a fancy way of saying one simulation with a bunch of scalar fields, all of which overlap. So, for example, in this ENSO-cosmology simulation, they were interested in 4 scalar fields: density, dark matter density, emissivity, and gray radiation energy. They wanted to show these at all the same time. Let's see if I can show this little video. This is work that Joe Inslee did a few years ago. So you can see that this is the same spatial domain and different transfer functions, different fields that we're looking at, and we want to see how they correlate. And this is actually fairly tough to do in a comprehensive way. And a lot of the time, scientists will just sort of eyeball it, and then they'll use statistical methods like looking at joint histograms to correlate the quantities independent of space. But the video is more for showing them, first, that their simulation's right, and second, that is sort of seeing high-level behavior in the filamentary structure of this cosmic web simulation. So a lot of current research in scientific visualization is around multi-fields, around this idea that a typical simulation, a typical physics code will run anywhere from a handful of variables to, well, in some cases with these Uinta simulations that Will and Dan and others have been working on, they're generating 130 fields or more. And you have to have some way of curating all of these and potentially tying them together in the same visualization. And that's a big challenge that we don't fully know how to do yet. And it's not just when you have different variables in the same simulation. Very often you'll have spatial quantities that overlap. So for example, each one of these are different molecular orbitals in a density functional theory computation. So these, roughly speaking, show the probability of an electron being in space at a given time. And if you combine them all together, you get this all-electron combined cloud. But this actually isn't very helpful. It just sort of shows you the overall blob, corresponding to the molecular simulation you're running. Ideally, you'd like to have some idea of where the bonds are. Right now, the techniques we have for visualizing these, just by showing them, are very much render it and see where things are. But we don't really have a more comprehensive way of saying we think there's a bond here because of the wave function that looks like this, let alone because of 8 separate molecular orbitals that look this way. And I actually don't have this graphic, but these are 8 of a 780 molecular orbital simulation. So you can see multi-fields are a big problem. So, and these are just 3-dimensional volume data with 1 or more fields. Really there's a whole spectrum where you look at dimension, so R2, R3, etc. on this axis, and then range, a dimension of the data type, so dimension of the tuple on the y-axis. And you can sort of think of different examples of where real-world scientific data would fit into these. So for example, a gas station along the road, knowing the x-coordinate of where that is, that would be a 0-dimensional range and 1-dimensional domain. Then you have the map of cholera in London. So most GIS would be 2-dimensional domain and 0-dimensional range. It's 0-dimensional because you either have cholera or you don't. Then you have temperature along a rod. It's a 1-dimensional rod, and it has a temperature value along various points. That's 1D range and domain. 2D domain and 1D range would be, for example, the height field of a continent, where all of a sudden it's a 2D map, but you have a height value, so a continuous value in the range. So if you go 2D and 2D, then you start to think about airflow, for example. So where all of a sudden you have a vector quantity at each point in space. So this is actually something that I should give you full disclosure. I borrowed this slide from Mariah's talk last year. But one thing that occurs to me is we didn't really discuss much about the difference between a vector quantity and tuples that are meant to be sort of condensed together versus tuples that are really multi-fields in their own right that are not supposed to be. So this is something that in Viz we have not really not really thought about maybe too much aside from the overall dimensionality of the range and domain. But yeah, going forward, 3D and 3D would be a 3D airflow in the atmosphere. So if you have a 3D vector field and a 3D volume, and then if you go up, you have a stress tensor and a mechanical part. So this would be tensor field visualization, would be higher dimensional than 3D in the range, then still 3D in the domain. And then most of what we're looking at is single scalar volumetric fields. So f of x, y, z, and that's h. So ozone in the atmosphere would be a good example there. And as Mariah pointed out in her slides, most of the time we're looking at this narrow box. And once you get out of this box, you get some very interesting domains of science. So, you know, I'd say going into the higher dimensional domain and then zero dimensional range, I'd say this is largely sort of InfoVis. Although actually it might be the other way around, InfoVis might be really 1D range and then higher domain. Depends on how you're actually considering range and domain when you start to talk about the general data visualization. Once you get to 1D domain and then 1D range and higher dimensional domain, where you might have 11 dimensions, that's sort of the realm of string theory and very exotic physics. And then you have lots of question marks where I can't even think of an example, but probably some mathematician would be able to come up with one. And then on the high end of the range axis, you have multi-fields of any domain dimensionality. And as I mentioned, these are really challenging problems, what to do with these data. So yeah, so we talked about the field, the concept of the scalar, vector, and tensor field, and what they look like. Now we're going to talk about how they're organized. And the reality is, when we talk about fields, it's more of a mathematical concept, more of an abstract concept, because the idea of continuity is really an illusion. All data are discrete. In fact, probably in the real world, all data are discrete. We're not quite sure how, but they are. And they're connected in a certain way, sometimes implicitly, sometimes explicitly. And these meshes, especially in computational science, are chosen based on what's most computationally efficient for the simulation. Looks like that got cut off there. And Viz software, the goal of Viz software is to implement a data model that handles a wide variety of field and some non-field data. And in a sense, you have a choice between visualization software that's tailored to a very specific problem and very good at doing that. So I would think of a lot of the implementations you're doing in D3 or something very specific like Images 3D's volume rendering software. I would think of that as a pretty good example of specific Viz software. And then on the other hand, you have general purpose visualization software like the visualization toolkit, which I'll go over in a few slides. And VTK, as I mentioned, is an example of a very general purpose solution for general scientific data. So up here you can see sort of a subset of the data that we deal with most commonly. We have regular grids, TET meshes, adaptive mesh refinements, so sort of block structured data, and then we have raw unstructured particle data. And I think this would be a good time to talk about structured versus unstructured, because in scientific viz, and actually in visualization and data science in general, you'll hear these terms a lot. Actually, quick show of hands, who's heard of unstructured or structured data? Oh, okay, all right.
But not in your interpretation.
Yeah, that's a very good point. So in general, when we talk about structured data from the relational database world, so this is probably the closest you can get to the definition. Structured data are indexed and can be accessed via some direct map or hash or array or query based on a data structure that is well laid out, well defined. So ideally, the search time for structured data would be constant or at worst log n. And unstructured data are data that are not indexed, where you really have to make your way through every single sample of data and find out if it's what you want and where to put it. So the idea is there that it's basically linear search time, very expensive. And I'd say in InfoVis and DataVis, Alex actually might correct me if I'm butchering this, but I'd say that's actually very close to reality in general purpose InfoVis and DataVis. Structured means you've already indexed it, you've already organized it, and that's exactly what you're doing in a sense in something like D3. You're taking something that is unstructured and you're structuring it in a way that D3 and your visualization can understand. And unstructured is everything else, miscellaneous text, imagery, video, etc. And you have to find a way to put that together and make meaning out of it. And in scientific visualization, well, the SciVis community has sort of made a mess of things. So the first thing to do is, before defining structured and unstructured data in SciVis, we have to differentiate between geometry and topology. So in scientific visualization, geometry is really position. It's really the set of vertices, the set of elements that you have and where they live in Euclidean space. And this really goes back to graphics and CAD disciplines, even before computer graphics existed. This idea of geometry, and not even how it's connected, but where points live in space. This is sort of the first core component. These data can be uniform, they can be structured, or they can be unstructured. And then you have topology, which is really a definition of the cells or the connectivity of the vertices. And these are a separate concept, and they can also be structured or unstructured. The end effect of this is that you have two separate definitions of data, and you can have structured geometry but unstructured topology, or structured topology but unstructured geometry. And whether data are unstructured or structured really is sort of on a case-by-case basis depending on both geometry and topology. So the most common data are uniform grids. So when we're working with volume data, these are 99% of the time what we're going to be working with. Certainly for this class, that's what we're going to be working with. It's also known as raster data. And structurally, this means that you have uniform spacing between the vertices. And what's great about this is that you don't need to store any sort of connectivity information at all. You just need to know the dimensionality of your data and which axes are fast, so short, and which axes are slow or long. And you still need metadata to know the dimensionality of the axes, as there's a sort of cautionary tale that we'll present in just a little bit. But the idea here in the uniform grid is the spacings are completely uniform. We don't need to store anything except for the data itself and the size of the axes. When we're talking about volume data, we very often talk about voxels. And a voxel, very simply, is one element, a volume element of a volume data set. The same way a pixel is an element of an image. And most of the time when a voxel will have, as an element type, it'll be whatever the field data is. So it can be a scalar field, so that means a voxel will have a scalar value. A vector field means a voxel will have a vector value. Now this gets a little bit confusing because unfortunately, the voxel is not well defined in the literature. You can have voxels with values at the center, and you can have voxels with values at the vertices. And then it actually gets even a little bit more complicated than that. You can have face-centered and cell-centered in addition, which is something completely separate. But in a nutshell, most of the time when we talk about voxels, we're talking about what's in the center of the volume element. And when we talk about voxel vertices, those are what define the voxel. So you would basically define your values here at these points, and then you would want some interpolation mechanism to reconstruct the value inside. That's the most common way of interpreting the concept of a voxel. So I was going to go back to the cautionary tale. The cautionary tale is the Arecibo message, which was a simple raster image transmitted from a radio telescope in 1974. that Frank Drake and Carl Sagan sent via transmission to a very, very far away galaxy, 25,000 light years away. Actually, I guess that's not even that far, like cosmology standards, but this was probably more a publicity stunt than any meaningful attempt to communicate with extraterrestrials. And in fact, it seems that Stephen Hawking says that this is a really, really bad idea if we actually do want to try to communicate with extraterrestrials. But the good news is that it's unlikely to succeed for many, many reasons. Well, the first is that probably the galaxy will have shifted by the time the data actually arrive at it, so it's not going to hit it anyway, probably. But the second is that if they do actually receive it, they'll have to figure out what to do with this raw raster data. And this raw raster data is being sent repeatedly as this encoding. So first they'll have to understand where the beginning, the end of the message is, and that might be a little bit challenging, but maybe they'll be able to figure this out and figure out that there are 1679 bits, which are the product of 2 primes, and they'll be able to figure this out. Again, they have no metadata, so they're going to have to come up with some way of figuring out that there are exactly 1679 elements, and these bits are 0 and 1. So maybe if they did that, they'd come up with a visual representation like this, like a supermarket barcode. And notice that 1679 is 23 by 73, and therefore maybe it's a 2D array, a 2D sequence that they want to look at as an image. So maybe they'll get this far and figure it out. Then they'll have to figure out, is it a 23 by 73 or 73 by 23 grid? And then additionally, is it which axis, is it slow to fast or fast to slow? And along the slow axis, do you look left or right or left? These are all conventions that we in graphics and image processing, we sort of take for granted, but an advanced civilization may have a completely different convention, a completely different way of doing it. So depending on what they come up with, they may or may not be able to make sense of this message anyway. So again, Carl Sagan said it was more of a publicity stunt than anything else, but the end effect is that without the metadata, even something where the structure is completely implicit, where the topology is completely unnecessary, even something as simple as a raster image would be very, very tough to decipher. And I cannot count the number of times where I've had to struggle and guess at the dimensionality of a data set. Is it 512 by 256 by 256 or 256 squared by 512? If you don't have the header and you don't know, you very often have to guess. This happens a lot. So that's probably the purest structured data we have. Then you have data that are structured and rectilinear, and these are but non-uniform. And these positions here can still be computed procedurally because you would have a list of the offsets along the x, y, and z axes for 3D data. And this is still purely structured data. It's just non-uniform. It's not actually as common. I think the only time I've run into data like this is some data wrangling work I did for Greg Foss of TAC, who did these very nice visualizations of turbulence in the ionosphere. So in practice, what this means, if it means anything, is that most of the time when you deal with uniform grid data, when you deal with structured data, most of the time people are talking about uniform grid data. Now, unstructured geometry. Now this slide actually, believe it or not, is the same slide that you would have for unstructured topology. Here we're talking about raw unstructured point data, where you actually need to store the XYZ positions of vertices. And there is no mesh. There is no well-defined connectivity between the vertices in space. Personally, I think this is one of the most exciting sources of data because some of the largest sources of scientific data at all in both the simulation and scan world generate point data. So we have cosmology simulations like HACK that are generating, now for their new runs, 30 trillion particles per time step. I mean, this is enormous, that you'd be easily in the high petabyte to exabyte range, depending on how you store it. And in practice, they don't store it. And you have also range scans, point clouds, LiDAR, also very large sources of unstructured, unorganized point data that are very challenging to visualize. And most of the time the way these are visualized is they're simplified down and we throw away the pieces that we don't want to see, we filter everything out, and we call it a day. But in practice, it would be very nice to be able to see the original data in full resolution and all its glory. And that's something that Will Usher and Ingo Wald at Intel is the first author, and I did recently in this work for Viz this year. We're basically rendering full cosmology simulations on a single machine with the right data structure. Structured grid topology. So here we're not talking about geometry anymore, which is the position of vertices. We're talking about topology, which is really the layout of the mesh. And the idea of topology is that you usually have a set of indices that tell you in which order the vertices are laid out. And then you'll have clockwise or counterclockwise. Counterclockwise tends to be the standard. And that's how you define a polygon. So it's actually very similar to what you do in 3D graphics for a triangle mesh, except here all of a sudden you might have higher order elements. Now the easiest way of doing this is actually not to have to store the topology at all, but to have the topology be implicit, even though you have unstructured geometry. So this would be unstructured geometry in this example on this slide, but structured topology. So a good example of this would be a finite elements or finite differences simulation on a curvilinear grid, where in space the points are going to spread out, sort of like in this image. But the topology of the simulation would be completely structured. So it's really just a big grid, and the cells just happen to be stretched in a certain way. And there are even more clever ways of doing this than curvilinear grids. There are spectral finite elements, I should say spectral HP methods are what they're called. So Mike Kirby and George Karniadakis of Brown, they're probably some of the world experts in these techniques. And the reason you would run these simulations, which seem fairly exotic, is that they give very good numerical results for, I guess, really for flow computations where precision is of the utmost importance. So you really care where your particle goes, and you want to make sure that nothing funny happens at a boundary of a mesh somewhere. So blood flow, special CFD applications. Yeah, so this is an example of one of the blood flow simulations using a spectral HP finite elements code. And the visualization was done by Joe Inslee at Argonne. The data came from George Karniadakis at Brown. And this is using a simulation code called Nectar. Now, when I searched for Nectar, all I could find was this 80s hairband. It might be the same guys, actually. Yeah, again, this is fairly esoteric stuff. I guess maybe less recently, but especially in the late 80s and early 90s, there was a lot of use of curvilinear grids for mostly CFD simulations that were looking at mechanical parts or airflow over vehicles or aircraft. So in the CFD world, I think curvilinear grids are still, at least, if not the standard, then at least fairly widely used. Because you'd want to use a curvilinear grid to represent something like the bottle of the body of the space shuttle. And the reason you do this is that your CAD model of the space shuttle actually is probably splined to begin with, and it has a sort of implicit curvilinear representation that you can just make into a mesh, and then you can run the simulation on the mesh. So moving out of curvilinear and exotic stuff like spectral HP, we have unstructured grid topology. So before we were talking about structured topology, now we're talking about unstructured topology. This embodies the vast majority of finite elements codes. So TET meshes, hex meshes, mixed elements, and it's easy to, I guess, understate how important these methods are to visualization in general. But I'd say the bulk of solid mechanics, CAD, as well as the bioelectric modeling that we do here at SKI, is really built on finite element methods. So just an enormous range of data comes from finite elements. So here we have some visualizations from Qubit. In the lower left, we have sort of a blurry image of the virtual soldiers in ski run. And we have everything from fan blades to manifolds to bioelectric simulations inside the human brain. All of these are modeled with finite elements. And they're very good. I mean, I think what happens with finite elements is that you can really, the geometry adapts to regions of interest in the simulation where you need to have a lot of precision. And the challenge is that your simulations then have to remesh all of this, but in terms of being able to run it efficiently without having to create a huge data structure, they're very good at that. So to summarize, for structured versus unstructured data, we have structured geometry versus unstructured or uniform geometry, and we can have structured or unstructured topology. If both are unstructured, then we're sort of into the raw points category. If you have structured geometry, it tends to be things more like rectilinear grids, and if you have structured topology, it tends to be things more like curvilinear grids and spectral HP finite element simulations. So if there's one take home, it's this slide. Usually in SciViz, when we're talking about structured or unstructured, we're talking about geometry. So usually when someone says structured data, they mean rectilinear grid, which doesn't necessarily mean uniform, but 99% of the time it will mean uniform. And unstructured is everything else. So not because it is well defined, but because we tend to go with the data we know. We tend to think of structured data as being uniform grid and unstructured as everything else. Technically, rectilinear grid is still purely structured data. So, structured or unstructured? Okay. Structured or unstructured?
Structured.
Unstructured. Wait. Oh no, you're right. Look at that. No, it's a hex mesh. It's still unstructured. Yeah. I don't think this is a purely curvilinear grid. Yeah, that one's weird. Structured or unstructured?
Unstructured.
Structured. Yeah, this is a CT scan of a human foot. You guys will get to render that pretty soon. Structured or unstructured? So without looking at the mesh, just based on which type of simulations would typically do airflow around a body with curved parts?
Probably unstructured.
Yeah, that's right. Okay, so in addition to the field data, we have non-field and other data. How are we doing on time, by the way? Oh, okay. So non-field data, these show up more often than I'd like to admit in visualization. So very often you'll have a boundary surface mesh that you want to show separately from the grid that you're doing the computation on. In molecular visualization, you'll have something like a wave function, for example, from a DFT computation, but you'll still want to show the atom geometry and bonds that are sort of the implied connectivity. Then you have things that are still more exotic. So you have secondary structures that you could show via ribbons. And then you can also have non-geometric annotations. And I'd say in GIS and in InfoViz, these are much more common. But in SciViz, they show up as well, where you'd like to be able to annotate something and put a marker in a volume data set. And the end result of this is that wanting to encapsulate both field data and non-field data, you end up with a data model that's fairly complex. Now we've talked about what the data look like. We've talked about fields, grids and meshes, and unstructured and structured data, and some non-field data. And we have the question of what do we do with it? And in computer graphics, it tends to be a very simple question of you have a mesh, you want to use OpenGL or some API to rasterize it, and then you're done. And visualization, especially scientific visualization, is really more than about just the rendering. Really, conventionally we think of it as being two separate processes, really three separate processes. You read the data, you apply some transformation or transformations to it, and then you render after the transformations are done. And that's sort of the conventional indirect visualization pipeline. The other way of doing it is direct visualization, in which you basically take the data and then you render that data directly. So volume rendering, for example, is what we call a direct visualization technique. And isosurfacing would be an example of an indirect visualization technique. So I'll go through marching cubes in the next lecture, but this is, I'd say, the canonical example of an indirect visualization technique, where you start with a scalar field, and then you're going to turn that scalar field into geometry of some kind, using an algorithm for converting, for example, a volume full of voxels into a set of triangles. And then you'll pass those triangles to OpenGL to rasterize them. And a direct visualization, it's in some ways simpler, in some ways more complicated. There you have the data directly, and you're going to apply a color map that will and some interpolation filter that will directly map values to pixels. And that's what you will do in the assignment, is volume rendering, so the direct rendering approach. And either way you do it, regardless of whether it's direct or indirect, there's still this concept of the visualization pipeline. The idea that data starts a certain way when you read it in, then you apply some filter to it, and then you render the results. And it could be that the filtering and rendering process are merged together somehow, but they still both exist. And it's still logically good to think of them as a chain of operations. So as a result, when you have more and more complex visualizations, for example, you are combining multi-fields together, you're applying transformations to certain fields, you're creating an algorithm that will filter out one field and convert it to something easier to look at. We tend to think of visualization as a workflow, like a flow chart, a tree, or a network. And the ski run is, I think, actually a very good example of the network, where it's still more or less a data flow that starts at a source and ends in a visualization at the end. But you can link nodes in this data flow together in ways that will somehow tie color to various simulation elements. And what's really nice about this is that in ski run it's really tied in directly to something like a finite element simulation. So you can actually run simulation and visualization and tie parameters together directly. So that's, I'd say, a very broad network-like data flow. ParaView, which is probably one of the state-of-the-art, or at least most commonly used tools based on the VTK, based on the visualization toolkit, it's a little bit simpler in terms of its workflow, in terms of its data flow. In ParaView, you basically start with a reader at the top, and then you have a simple sequence of filters, and then the last filter ends up being what you render. So that's probably more of a tree diagram, and you can sort of see the tree in the left bar over here, and the sidebar. And ParaView is difficult enough to use, and it's tough enough to figure out how to actually organize your filters and where a visualization came from, that there have been tools that have been built around this idea of provenance, this idea that you don't really know what set of transformations you've applied to your data to get from raw raster data to this particular isosurface. And provenance, so this is a tool called VizTrails that was developed by Claudio Silva's group, actually back when he was still at University of Utah, but it's continued to be in development since he moved to NYU. It's really built around the idea that you can take any visualization workflow tool, like VTK or ParaView, and you can tie to VizTrails, and VizTrails will remember the settings and the transformations that you made to the data. and we'll keep track of them so that they'll be fully reproducible. So in principle, you shouldn't need to have two separate applications. In principle, provenance would be built into every workflow. But in practice, that's hard. So we tend to go for other solutions. So the assigned reading that we had for tonight, for last night, was an overview of the data model and the visualization toolkit. This overview was written by Stefan Berger back when he was at Vienna. VTK is probably the closest thing we have to a one-size-fits-all comprehensive data model and visualization platform for scientific visualization. What's great about it is not that it's the fastest or the best at any one problem, but you can use it for a wide variety of problems and almost always find a way to get some visualization out of VTK without having to write your own code from scratch. You will have to script, but you won't have to write C++ code very often. It's a full-fledged data model for structured and unstructured and particle data. It supports tet meshes, hex meshes, everything you'd want. And you don't have one format for tet mesh and another for hex mesh. You just have standard VTK data. You have an object-oriented hierarchy where all VTK data ends up being encapsulated in the same data model. And if you read the assigned reading, you'll see that VTK has this difference between the element and the data itself, which I'll actually go over in just a slide, in one slide here. It has hundreds of readers and analysis filters, and it's been developed for upwards of, I think, probably about 2 decades now. And the idea is that you would call this from your own visualization code, and if you don't want to write it in C++, you can use Python or Tcl or NTK to do this. The downside is that there is no UI for VTK by default, so you need to code one. Or you can use a sort of provided UI like Paraview to do that. There's no distributed rendering, so if you have multiple nodes in a cluster and your data is too big to fit on one machine, VTK won't solve any problems for you there, but there are tools like Paraview and Visit that will. Until recently, VTK did not support any of the latest OpenGL even 2 features. So it was fairly brute force and inefficient at doing things. On the other hand, it's supported by pretty much every machine out there. And the last thing I'll mention is that even though the data model is comprehensive, you can really squeeze anything, including spectral HP methods, into the VTK data model. The filters and renderers may not know what to do with it. So if you do manage to use the data model to represent your data, you still might have to write your own filter to do something with it. And lastly, there are a lot of cases, for example, especially with structured data or fast query structures, where you might want to do something that would be fairly heavyweight in VTK and would require a lot of not just software engineering, but a lot of inefficiency in memory usage and performance. But the great thing about VTK is that it nearly always works. So it's probably been the standard bearer for general purpose scientific visualization for at least the last 10 years. So cell types in VTK. So VTK has 2 concepts. It has cells and attributes. And attributes is sort of like the element in the field that I talked about before. So you can have scalar, vector, tensor. You can also have more exotic things like text or coordinates. And cells are, they're sort of like the geometry concept that we mentioned earlier, except they're sort of like one element of the mesh that you would have. And between cells and attributes, you basically can put together any sort of data model you want, representing geometry and topology, and the concept of the element. I guess the topology, in a sense, tends to be composed of cell types and written by the programmer himself, or more often the VTK team, to sort of fit into the canonical VTK classes like VTK image data, VTK unstructured grid, etc. But it's all there. And if you take a look at the assigned reading, you can see a very simple Marching cubes isosurface example in VTK. You start with a reader, you read in structured points data, then you apply a contour filter to it, so this is going to use the Marching cubes algorithm. And that's going to output poly data, so triangles, and then you'll have a mapper for that poly data, the mypoly data mapper, and that will essentially render the Marching cubes, the output of the Marching cubes algorithm. So that's without using ParaView or a tool like this, that's how you use VTK manually. Yeah, so I guess before I go on too much, I'll talk about what we do in practice inside Viz. So in practice, that chart where we have the domain and range, the n by n domain and range, we do tend to only look at 2 narrow columns and maybe 3 rows in that chart. But really, that's maybe a very arbitrary classification. Really, in scientific visualization, we tend to have certain problems that come up again and again and again for which there are very well-known solutions. So I think of volume rendering, medical data or simulation data. Scalar field volume rendering is one of those problems where the solutions are fairly well known by now. In GIS, you have heat maps, you have glyphs that you can use, you have height fields, and in molecular viz, they have their own set of standards that they use. For example, ball and stick or ribbons, and so scientific visualization tends to be very domain specific. Instead of having one tool set like VTK that everybody does everything in, we tend to have lots and lots and lots of different tools that are really tailored to a specific task and have their own vocabulary. And probably, certainly for Janet Awas's talk, but in the last 3 talks that I'll be giving, we'll be talking more about special case algorithms and techniques and less about what you would do in VTK specifically. So I'll give a quick preview of homework 6 now. In homework 6, you are going to write your own volume renderer in WebGL and JavaScript. And you're going to use the work you've already done in D3 with polylines to write a 3D transfer function editor, create D3 data that's then tethered to a 2D texture in WebGL. And a lot of this code will be given to you, so you won't be completely fumbling as to how to do it. I found it very tricky, as a full disclaimer, until Alex Bigelow showed me how. But we'll try to make that as accessible as possible in terms of getting the data from D3 into a 2D texture. And as extra credit, so you will be responsible for writing the volume integration itself, which I'll go over in the next lecture. But as extra credit, you can apply gradient and Phong lighting to the volume, which makes it look a lot fancier and also makes it quite a bit slower. And here I'll show a little demo of it. Hopefully, yeah, oh yeah. So this is the WebGL volume renderer. And this is just an example transfer function editor. So we don't expect exactly this. There are many, many different ways of doing transfer function editors, and actually we'll show some of the other alternatives in next class when we talk about volume rendering. Actually, maybe even this class, depending on how we're doing on time. I think we're almost out. Yeah. But you can see you're able to move vertices around, and this changes the transfer function. And basically, you will be given not the full volume rendering solution, but what we call pseudo-color plot, which is just the outside of the box. Then you'll have to reproduce the volume renderer inside and create a transfer function editor. And here you can see we have lighting, so without lighting it looks a little bit more flat and just like a bunch of blended colors. That's, we'll have this posted.
You want to show the second data set?
Oh yeah, sure. So this is the foot. Remember the data set that I asked if it was structured or unstructured? obviously the teapot. So this is a teapot with a lobster inside. So one thing I should note is the aliasing artifacts that you'll see for a lot of these data sets are peculiar to how we had to do 3D texture interpolation for this assignment. How many of you have read the assigned reading on volume rendering from real-time volume graphics? Show of hands. Oh, go. That's okay. Read that if you want to make your life very easy for the assignment. And if you're really curious as to why we have these weird banding artifacts in this WebGL implementation, read chapter 4, which will talk about the old bygone technique of 2D texture slicing. So in a sense, using WebGL, we're sort of reproducing techniques that were popular circa 1999, but in slightly different ways from how they would have done it in 1999 also. But yes, read the 2D texture slicing, and that will give you a good idea of what the sample as 3D texture function in the homework assignment is doing. Ideally, you would actually write, if you didn't have any 3D interpolation, you would actually write something a little bit like this, where you're doing trilinear interpolation as just a sequence of 7 linear interpolations. And that's really fun code to write. But unfortunately, it doesn't support, WebGL does not support 1D textures, so this didn't work. So let's see, we have until 10:30?
Yeah.
Okay. So yeah, the next lecture, so I guess I will go into interpolation a little bit, and I might get cut off a little bit early. But I wanted to make sure that I had time to show off the reference solution for the homework. So interpolation. So I mentioned before that all data are really discrete, and this concept of continuous data is really just something that makes our lives easier, both in terms of how we compute the data and how we interpret it. But the real question we have is if we want to see continuous data, if we are truly considering this data as a continuous scalar field, how do we do that if we just have discrete data that exist at vertices of a voxel, or at vertices of a tet mesh or hex mesh or what have you, or even raw unstructured points? And this is what interpolation is trying to answer. So there are two sort of separate questions here. And one's the choice of sampling, which is where you actually place a sample and want to make the measurement of what the field value is of that sample. And the other one is the question of interpolation, which is how you actually do this mathematically, how you would actually reconstruct this value based on the mesh around it or the vertices around it. And there you're really taking into account both what you'd like to do from the simulation or the scan source, and also how the data is laid out. Is it a tet mesh, hex mesh, uniform grid, etc. So the idea is that you want to go from Rn to Rm, and so that's from domain to range. It's this f of xyz goes to value. And this is really what interpolation is trying to do. The other thing I should mention is that there's a difference between interpolation techniques, which essentially take a set of values that are weighted and have a support filter around them. And there are also approximation or extrapolation techniques, where you're going to weight them in slightly different ways that are not going to actually necessarily give you a continuous field when you do the reconstruction. In practice, they very often do, but there are techniques, for example, moving least squares or radial basis functions that we can use for approximation, but a lot of people would not consider them to be an interpolation filter in their own right. The simplest way of doing interpolation is to just look at the nearest neighbor, the vertex that's closest to you. So here in 1D we have 5 values, 5 vertices, and we want to know what's the value of I, the image, at 1.3. So here we would, there are actually 2 ways of doing it. There's using the distance to the closest vertex, and more commonly we just truncate or round down, and there we would say it's I of 1, and that would basically be the end. So you'd say I of 1.3 is 1 in nearest neighbor interpolation. Now in linear interpolation, this is probably the most common by far. We have a one-dimensional, we still have a 1D example, and we want to know what I of 1.3 is. And here what we've really done is we have a series of tent filters. So the filter is basically 1 minus x on the negative portion of the ramp, and then, I'm sorry, it's 1 minus x on the positive portion of the ramp, and then x in the negative portion. And that's the tent filter. And you're going to evaluate that tent filter for the 2 closest vertices in this case. So at I of 1 and I of 2. And when you do that, you're going to take the formula. So it's 1 minus x times I of 1 and plus x times I of 2. And when you do that, you end up with a result, which is 1.3. So bilinear interpolation is really just 2 successive linear interpolations. It's really summing 2 linear interpolations together. So we're interpolating first along the x-axis, and then we're going to interpolate along the y-axis separately. This is maybe a little bit more complicated than it needs to be in this example. Actually, a much better way of thinking of it is, I think, looking at this pseudocode right here. And bilinear interpolation is really just the last 3 interpolations in this trilinear interpolation example. But another slightly more intuitive way of thinking of bilinear interpolation is a weighted sum of the 4 pixel values. So if you have these 4 values, you're taking a sum of the 2D weights of all 4 of these vertices. And this is a visual representation of what that looks like. And then trilinear interpolation, you're doing the exact same thing, except instead of having 2 axes, you all of a sudden have 3. So all of a sudden you have weights for 8 vertices that you need to worry about. And these weights are, again, the trilinear interpolants of x, y, and z axes. And this is actually my favorite formula for how to do trilinear interpolation. It's just the sum of 8 voxel values, and you multiply the xi, yj, zk components together, and you have, and the x0 and x1 are really just the separate parts of the tent filter. So if you wanted to do this for a B-spline filter, you would have 64 points instead of just 8. Here we just have 8, and the ij and k values are really just showing the different parts of the filter. So, really in a general filter, you replace the xi, yj, zk by some general theta, which is the basis function, and that theta would be a function of 3 dimensions, depending on what your filter looks like. So this is, I say, this slide and this last 7 successive linear interpolations are, I think, the easiest way of thinking of linear interpolation. And what's interesting is that you can also do, looks like that slide kind of got cut off. Not just trilinear interpolation, but you can do higher order interpolation, where instead of having a tent filter, which is really just this the x and 1 minus x, you could have a higher order spline that's defined over a wider stencil. for example, a 4-point stencil. And if you do that, you can end up with higher reconstruction fidelity and renderings that look much, much, much nicer. You have to take care that the scientist actually wants to see this, but that's generally, I've never had anyone complain when I showed them results from B-spline filtering in a volume renderer. And yeah, that's, I'd say, interpolation in a nutshell. Thanks.